have looked into crystallographic directions so far. Today, what we'll be doing is how to identify the crystallographic planes. How do we represent a plane in a unit cell? It says that in the orientation of planes for a crystal structure, the unit cell is the basis with three-axis coordinate system. That means you have to represent a plane whether in the form of numerical digits or whether pictorially or graphically in all but the hexagonal crystal systems. Except for the hexagonal crystal system, crystallographic planes are specified by three Miller indices known as HKL. So Miller indices represented by curvy brackets HKL, three digits, would represent a crystallographic plane in all the crystal structures except for hexagonal crystal systems. We'll see why it is different in hexagonal crystal systems. So how do you identify a plane, or how do the three digits HKL basically represent a plane in a unit cell? We'll see the procedure how to identify a plane. So the procedure to determine HKL, how do you find the HKL for a specific plane? I'll discuss the procedure. Let's say I have a cubic unit cell. This is my unit cell, and I'll take the simplest plane. Before I take the plane, I'll specify my axis as this is positive y-axis, this is positive z-axis, and this is positive x-axis. And let's say I draw a plane or a highlight a plane. This is my origin, and I select this plane. This is the plane I am interested in. Let me draw the boundaries of the plane in a different color so that it is visible to you. So I am interested in the bottom plane. Let's say someone has drawn this plane for me and he wants me to find out or represent this plane in terms of Miller indices H, K, and L. So what is the procedure to find out the HKL for this plane? The procedure says that the first thing you have to check, if the plane passes through the selected origin, which is O, you should draw either another plane which is constructed within the unit cell by an appropriate translation. That means, sorry, I have not. So this is the complete unit cell. All right. So the first thing is, if the plane that you have selected is passing through your origin, either you select a new origin within this unit cell so that the plane is not passing through the origin, or what you have to do is that you translate this plane by an appropriate translation, so that let's say I translate this plane. Right now, is the plane passing through the origin or not?
Yes, sir, passing.
Yes,
So
sir. Sir.
what I'll
One
do
of
is
it
that
is
I'll select another plane which is translated by the exact amount of the unit cell dimension. So I have moved this plane upwards by a complete unit cell dimension, which is this plane, the yellow plane. Clear enough?
yes, sir.
All right. This is one way of doing it. Another way is I can change the origin also. I can move the origin. Instead of having the origin at this point, I can have the origin at this point also. But either one of them, so that the plane does not passes through the origin. At this point, the second thing that you have to do, once you have made sure that the plane is not passing through the origin, the second thing that you have to do is that at this point, the crystallographic plane either intersects or is parallel to each of the three axes. So if I have moved this plane, the yellow plane now, so this is no more the plane. Essentially, let me draw the axis once again. Essentially, what has happened is that now my plane is not passing through the origin. This new plane, this is positive x-axis, this is positive z-axis, this is positive y-axis. It would either be intersecting a axis or it would be parallel to an axis. Now you have to determine the intercept for each axis in terms of lattice parameter A, B, and C. So this yellow plane, let's first take X, Y, and Z and write down the intercepts. Is the yellow plane uh, intersecting this x-axis?
No, sir.
So I'll write over here that it is not intersecting. That means this plane is parallel to x-axis. So I'll write the intercept as infinite. Since the plane is not cutting the x-axis, I'll write the intercept as infinite. Now, is the plane intercepting this y-axis?
No, sir.
No. No, sir.
So I'll write the intercept as infinite. Is the plane intersecting the z-axis?
Yes, sir.
Yes, sir.
Yes, sir.
And it is intersecting for the complete length C? Or let's say A.
Sir, can you please repeat that?
जो इंटरसेप्ट हो रहा है वो यूनिट सेल की कंप्लीट लेंथ के साथ हो रहा है ना. इफ आई टेक दिस एज माय ओरिजिन, इफ दिस इज द ओरिजिन, तो यहां से लेके यूनिट सेल का जो एज है वहां पे इंटरसेप्ट हो रहा है ना एट दिस
Yes,
पॉइंट.
sir. Yes, sir.
So
Yes, sir.
this is termed as 1 since it's complete one unit dimension for the unit cell. Clear enough?
Yes.
So I'll write the intercept as 1. ठीक हो गई बात? Is it clear?
Yes, sir.
Yes, sir.
Now, once you have found out the intercepts, what you will do is that you will take the reciprocal of intercepts. So 1 over infinity, 1 over infinity, and 1 over 1. This would come out to be 0, this would come out to be 0, and this would come out to be 1. Clear enough?
Yes, sir.
All right. Now, in case once you have taken the reciprocals, so the third point was the reciprocals of the intercepts are taken. A plane that parallels an axis may be considered to have an infinite intercept and therefore a zero index. So since x and y were axes were parallel to the plane, the reciprocal of the intercept is 0. It further says if necessary. In this case, this is not necessary. If necessary, these three numbers are changed to the set of smallest integers by multiplication or division by a common factor. Since the fourth step is not necessary in this case, since all the three digits are in integers, you would write these three integers 0, 0, 1 as the Miller indices for this plane. It is known as H, K, and L. Clear enough?
Yes,
Yes,
sir.
sir.
All right. Now let's look at few of the planes. I had this unit cell with me. This was the unit cell. This is my origin. This was the plane. Now, since the plane was passing through the origin, I shifted my plane upwards. This was the plane, and the HKL or Miller indices for the plane with regards to the origin O is 0, 0, 1. I could have also shifted the plane to a bottom plane. This would also be an equivalent 0, 0, 1 plane. Although you would have 0, 0, 1 bar, since the intercept would be in the negative Z direction, but it is essentially the same plane. The three planes are essentially the same planes. Clear enough?
Yes, sir.
Yes, sir.
All right. Now let's look at another plane. This is the plane. Now, having O as the origin, if I write down over here X, Y, and Z, the first thing I made sure that the plane is not passing through the origin, so I don't need to move the plane or the origin. None of or either of the two should not be moved. Now, if that condition is satisfied, I move to the second step and I find out the intercepts of the plane with the x-axis. The intercept for the plane with the x-axis is 1. The intercept of the plane with the y-axis is essentially 1. And the intercept of the plane with z-axis is infinity, since it is parallel to the z-axis. I take the reciprocal. When I take the reciprocal, this would become 1, this would become 1, and z would become 0. Now, since they are already in the smallest integer form, I don't need to follow the fourth step, and I would straight away write the plane as 1, 1, 0 plane. Clear enough?
Yes, sir.
Yes, sir.
And the three planes are equivalent planes. They are parallel equivalent planes. I hope this is clear to you.
Yes, sir.
All right. Now let's look at another plane. If I look at this plane, you see this plane is not also not passing through the origin. So if I write down the intercepts at x, y, and z, now you tell me the intercept at x-axis.
Sir, one.
1. The intercept at y-axis
Sir, one.
Sir,
1, sir.
1.
and the intercept at z-axis
Yeah, 1. Infinity.
Sir,
Infinity, sir.
1.
1. So if I take the reciprocal, it would still remain 1, and I can write the
Yes,
plane
sir.
as 111 plane. So 111 plane refer to the origin at point O. Clear enough?
Yes, sir.
All right. Now moving on, I have this plane over here. I want to find out the indices for this plane. So what do you think? This plane is passing through the origin O. All right. So what I'll do is that I'll shift the origin to this point, O bar. So my new axis would become, this would be my positive Z axis, this would be my positive Y axis, and this would become my positive X axis. Now if I look at this plane and I write down X, Y, and Z, is the plane passing through the or intersecting the x-axis, the positive x-axis, the newly drawn positive x-axis?
No, sir.
No, sir.
So
No,
I'll
sir.
write infinity. I'll write infinity. Is the plane intercepting my y-axis?
No,
Yes,
sir.
sir. नहीं z एक्सिस को सर कर रहा है.
This is my negative y-axis. Is it intercepting my negative y-axis?
Yes, sir.
किस जगह पे इंटरसेप्ट कर रहा है?
सर -1.
Sir, origin पे.
-1. -1. Is the plane, let's say this is half the cube length, is the plane intercepting my z-axis?
Yes, sir.
Yes, sir.
Yes, sir.
What is the point?
Sir,
1 by
1
2.
by 2.
1 by 2. Now, you would take the reciprocal of the 3, x would become 0, y would still remain as -1, and z would become 2. So
2.
you could write the Miller indices of the plane as 0, 1 bar, 2. So this is a 0, 1 bar, 2 plane as it is shown over here. Clear enough?
सर
जी
सर ये 1 और 2 हमने assumption ली है.
नहीं, ये मैंने आपको बता दिया ना कि इंटरसेप्ट हाफ पे कर रहा है.
अच्छा आपने बता दी. सही है.
ठीक है, ये आपको बता दिया
जी.
मैंने. जैसे
ठीक.
यहाँ पे ये बताया हुआ c/2 पे इंटरसेप्ट कर रहा है. क्लियर?
Yes sir.
All right, all right. So the procedure is given over here. You can always refer back to the procedure. Now let's look at the situation in a reverse order. You have been given a plane with the Miller indices 0, 1 bar, 1 within a cubic unit cell, and you have to draw this plane. Now this means that the intercept at x-axis is infinity. This means that the intercept at y-axis is -1, and this means that the intercept at z-axis is 1. So let's draw this plane. If I have this as my cubic unit cell, I'll take the intercept over here as -1 along the y-axis, and I'll take the intercept over here as positive along z-axis, and I'll draw a line. Now this plane would have the same line over here, drawing like this, and this would become my plane. This would essentially be my plane. This plane would essentially be not crossing the x-axis. To have a better view, this is your plane. Cutting the y-axis at -1, cutting the z-axis at 1, and being parallel to the x-axis. All right?
Yes, sir.
Yes, sir.
All right, great. Now, for hexagonal crystal systems, for all the other crystal systems, the Miller indices are HKL, 3 Miller indices. For crystals having hexagonal symmetry, it is desirable that equivalent planes have the same indices as with directions. This is accomplished by a Miller-Brave system. That means since hexagonal systems have 4 coordinates axes, so you would need to have 4 index system HKIL scheme. That means, for example, if I say 111 plane in HCP system, if I say 111 plane in HCP system, essentially there should be a mechanism to convert these HKL 111 indices to HKIL 4 coordinate system in HCP systems. The conversion is very easy. The only thing is that the new letter I or the new index I that is being introduced, it is essentially the negative sum of the first 2 indices. H plus K having a negative sign would give you the I index. For example, if I say, how would I represent 111 plane in a Miller Brave system or 4 index HKIL system? So I would have H the same way, K would be the same, I would essentially be 2 bar, and L would remain the same. So only this would add up for a 4 index system in terms of I, which is the negative sum of H plus K. Clear enough?
Yes, sir.
Yes.
All right. Now let's look at the different planes in a hexagonal crystal system. Let's say this is let's say this is my origin. This is positive A1. This is positive A2. This is positive A3. And this direction is essentially positive Z direction. Now, let's look at this bottom plane, 0001 plane, this plane. If you look at this plane, is the plane passing through the origin?
Yes, sir.
So you will have to move the plane or the origin. I find it easier to move the plane. So I'll move the plane upwards, the plane by a unit cell complete unit cell dimension. So this plane is moved upwards. Once this plane is moved upwards, uh, is this plane intersecting any of the positive axes A1, A2, A3?
No, sir.
नो सर
So,
सर
so
सिर्फ जेड
A1.
एक्सिस को कट करेगा
जी बिल्कुल A1, A2, A3 and Z. This would be infinity, 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 and Z axis it is cutting at 1. So you'll have 0, 0, 0, 1. That means the Miller indices would be 0001 for the same plane. Clear enough?
Yes, sir.
All right.
Yes,
Now
sir.
let's look. G. Let's look at another plane, which is this plane. Is the plane passing through the origin?
No, sir.
No, sir.
So if the plane is not passing through the origin, let's look at the intercepts A1, A2, A3, and Z. So if I draw negative Z axis, negative A1 axis, negative A1, is the plane cutting negative A1?
Yes, sir.
यस सर
Yes,
sir.
sir.
Minus 1. This is A2 axis. Is the plane cutting positive or negative A2?
No, sir.
No,
No,
sir.
sir.
So infinity. Is the plane cutting A3 axis?
Yes, sir.
Yes, sir.
Positive 1. Is the plane cutting Z axis?
No, sir.
No, sir.
So essentially you'll have minus 1, 0, 1, 0. That means minus 1 bar, 0, 1, 0. This would be the plane represented by the black color. Clear?
Yes, sir.
Yes,
Now
sir.
let's
सर
look at
इन्फिनिटी से
another
क्यों
plane.
रिप्रेजेंट करते हैं
Ji, sorry?
सर इन्फिनिटी से क्यों रिप्रेजेंट करते हैं अगर किसी प्लेन को कट ना कर रहा हो
Beta, did you join late?
यस सर
Beta, go back and see the recordings. All right?
यस सर
इसलिए करते हैं क्योंकि अगर प्लेन कट नहीं कर रहा तो इट इज essentially parallel. When would you have a plane and a line not intersecting each other? Only when they are parallel to each other. All right?
यस
So
सर
if the plane is not intersecting, it's essentially parallel. And parallel is represented by clear.
यस सर गॉट इट
And try to try to be on time, please. Now let us look at this plane. And have the coordinate axis A1, A2, A3, and Z. Is the plane cutting A1 axis?
Yes, sir.
Yes, sir.
Yes, sir.
Is the plane cutting
यस सर
A2 axis?
No, sir.
यस सर
No.
All right, tell me where is it cutting, beta?
वो सोचा वो उसके नीचे से पास कर देगा
G bilkul. So it is not cutting its infinity intercept. Is it cutting the A3 axis?
Yes, sir.
सर नेगेटिव A3 को कट करेगा आई थिंक
नो सर
Sorry?
सर नेगेटिव A3 को कट करेगा ना
Yes, very good. Negative minus 1. Is it cutting the Z axis?
No, sir.
Yes, sir.
नो सर
No, sir.
This is the plane. This is the line. This is z-axis going on. Is it cutting the z-axis or not?
Sir, cutting.
Sir, yes, sir. Cutting.
किस जगह पे कट कर रहा है?
1/2 पे
ये लाइन नहीं गुजर जाएगी सर, जिस तरह की
जी सॉरी,
प्लेन की शेप बन, सर इसकी बैक साइड से नहीं गुजर जाएगी लाइन जेड एक्सिस?
वाई?
सर जिस तरह की शेप बनी हुई है इसी तरह लग रहा है सर।
अगर यहाँ से
तो
लेट
कंप्लीटली
से
Z पे लाई नहीं कर रहा।
just give me a minute. All right, let's say कोई प्लेन यहाँ से शुरू होता है. Let me take another color. All right, let's say कोई प्लेन यहाँ से शुरू होता है. A plane is starting from this point and it's moving in this direction, growing in this direction. और ये आपका सेंटर यहाँ पे इस प्लेन का सेंटर है. This is the center of this plane. Z एक्सिस इन दोनों के दरमियान में है. Z एक्सिस इस तरह आ रहा है. ये प्लेन जो यहाँ से ग्रो होता हुआ जा रहा है, क्या उसको कट किए बगैर गुजर जाएगा?
नो सर।
नो सर।
और आपको शो क्या किया जा रहा है? ये लाइन शो किस प्लेन पे की जा रही है? ये जो प्लेन की लाइन है शो किस प्लेन पे की जा रही है? इस बेसल प्लेन पे की जा रही है ना. तो ये प्लेन जब ग्रो हो रहा है तो इसका इंटरसेप्ट जो है वो z एक्सिस के साथ कहां पे बन रहा है? If this is the center of the top plane, ये जो प्लेन ग्रो हो रहा है इस प्लेन की ये एक बाउंड्री आपको शो की गई है. ये बाउंड्री आपको टॉप प्लेन पे शो की गई है. वन थिंग यू नो इज दैट अगर प्लेन ग्रो हो रहा है इस डायरेक्शन में तो डेफिनेटली z एक्सिस को कट करेगा. ग्रोथ ऐसा हो नहीं सकता कि ये प्लेन ग्रो होता जाए इस डायरेक्शन में और z एक्सिस को कट किए बगैर निकल जाए. सवाल सिर्फ ये है कि वेदर इट इज कटिंग द z एक्सिस ओवर हेयर, ओवर हेयर, ओवर हेयर, या कहीं बाहर जाके कट कर रहा है. अगर ये लाइन आपको दिखाई हुई है टॉप प्लेन के ऊपर तो ये कट किस जगह पे करेगा?
वन पे.
ऑब्वियसली अगर प्लेन का एज आपको दिखाया हुआ है टॉप प्लेन के ऊपर तो इसने कट करना ही इसको 1 के ऊपर है, सेंटर में कट करेगा. इज दिस क्लियर? ये नहीं है?
Yes, sir.
All right, so for a1 it is 1, for a2 it is 0, for a3 it is -1, for z it is 1. Taking the reciprocal, infinity, taking the reciprocal, it would be 1 0 -1 1, or 1 0 1 bar 1 in the square, in the curly brackets. That would give you the Miller indices for the plane. Clear enough?
Yes, sir.
All right.
Yes, sir.
Moving on, let us look at linear and planar densities. Linear density is defined as the number of atoms per unit length whose centers lie on the direction vector for a specific crystallographic direction. Number of atoms centered on direction vector divided by the length of direction vector. The units are atoms per Newton meters or atoms per meter, depending upon what is the length that you are dealing in, the units of the length. So let's say we have to find out the linear density, number of atoms per unit length, along the direction 110 for FCC crystal structure. So if you have this FCC crystal structure, the 110 direction is this direction. This is 110 direction, 110 direction with X as the origin. And you have to find out the number of atoms sitting on this direction in this unit cell divided by the length of the line. So accounting the sharing of atoms with adjacent unit cells, X and Z, they are being shared by 2 unit cells along the same direction. Along the same red line, they are being shared by this unit cell as well as a unit cell which is adjacent to it. All right. The same atom would be shared by another unit cell which is adjacent to it along this direction, red direction. Clear enough?
Yes, sir.
Similarly,
सर ये
this
रिपीट
X
कर दें
atom,
प्लीज.
G. So this Z atom or X atom, they are shared by uh, adjacent unit cell along this direction. So if I have this direction over here, another unit cell would be over here, and this atom would be shared by sorry, I'm just let me draw it again. So if you have an atom over here, this atom would be shared by another adjacent unit cell along the same direction. So if you have this direction, this atom is shared by this unit cell and this unit cell along the same direction. Clear?
Okay, sir.
All right. Similarly, the X atom would be shared by this unit cell and another one over here in this direction which is adjacent to it. So the contribution of X and Z atoms would be half, and the atoms Y would entirely lie within this unit cell along this red direction. So an equivalent of two atoms would lie along the 110 direction vector in this unit cell. And the direction vector length is 4r. You already know that the diagonal length in an FCC is 4r. So your linear density along the direction 110 would be two atoms divided by 4r or one atom divided by 2r. This would be the linear density for an FCC unit cell along the 110 direction. All right. Now moving on towards the planar density. Planar density is taken as the number of atoms per unit area that are centered on a particular crystallographic plane. And this formula is the number of atoms centered on a plane divided by the area of the plane. Units are atoms per meter square or atoms per Newton meter square. Planar density of 110 plane for the FCC crystal structure. So we have to draw 110 plane within an FCC unit cell. This is 110 plane in an FCC unit cell with regards to this as the origin. Now, if you see, there are 1, 2, 3, 4, 5, 6 atoms that are lying on this plane. But once I look at the planes, this is the same plane which is in another unit cell. Again, the same plane in the unit cell which is on top of it, another plane which is on top of it. So this corner atom is essentially shared by four planes in four different units, four same planes in four. It is being shared by similar plane in four other unit cells. So the contribution of this corner atom to this plane would be 1/4. So all the corner atoms would have the contribution of 1/4. However, this atom would have the contribution of 1/2 because it is being shared by the unit cell which is on top of it and the unit cell which is this the shown unit cell. Along this plane, the contribution is half. If you want to have a clearer look, you see this is the plane. The contribution of the corner atoms would be 1/4 and the contribution of central atoms would be 1/2. towards the plane in this unit cell. So it says 1/4 of each atoms A, C, D, F, and 1/2 atoms B. They would contribute to this plane in this unit cell. So the equivalent of 2 atoms are on that plane. Now, how do you find out the area of the rectangle so area of the plane? You know that this length is 4r. This length is 4r, and in an FCC, this length is a, which is equivalent to a is equivalent to 2 under root 2r in an FCC unit cell. So essentially, the length, the horizontal dimension is 4r, and width, which is the vertical dimension, is 2r under root 2 because it corresponds to an FCC unit cell edge length. So the planar density for the plane 110 is essentially 2 atoms divided by 8r square under root 2, which is 4r multiplied by 2r under root 2. This is the planar density. All right. Moving on towards the last concept of how the stacking sequence is situated within the crystal structures, we know that the closest packed planes are FCC and HCP, both having the atomic packing factor of 0.74. So let's say in an HCP, the the basal plane, it is closely packed. This is the closest they can get packed in an HCP crystal structure. As I'd already mentioned, there are two sort of cavities, one which is facing upwards, the other which is facing downwards. The second layer in an HCP would either occupy the upward cavity or the lower cavity. So the closely packed first layer is termed as layer A, which is this layer. On top of it, in an HCP, there comes another closely packed layer, which would either occupy the cavities which are facing upwards or the cavities which are facing downwards. So this is the second layer which is coming up, and it has essentially occupied the cavities which are facing upwards. This is the second close packed layer, which is termed as layer B. Now for the third layer in an HCP, it would come directly on top of layer A. This is layer A. So in an HCP crystal structure, the stacking sequence of atoms in close packed direction is A, B, A, B, A, B. And the close packed plane, if you see the closely packed plane, the atoms which are closely packed, the closest packed atoms are in layer A, or you can refer this to as the plane 0001 plane. This is the plane in HCP which is the closest packed plane. I hope it is clear to you guys. Is it?
Yes, sir.
Yes, sir.
All right. Moving, so in HCP, the atomic packing factor is highest, 0.74, and within HCP, it is this plane, which is layer A, or 0001 plane, which is the closest packed plane. We'll come to know of the importance of close packed planes later on when we'll see deformation. But you need to understand that this is the closest packed plane in HCP. Similarly, FCC has the similar atomic packing factor. So we need to understand what is the stacking sequence in FCC and which is the closest packed plane in FCC. So let's say in FCC, this is the bottom layer. This is the first layer, close packed planes, close packed atoms in a layer. Now, this is termed as layer A. If you see, now the second layer has to come on top of it. There are two sort of cavities. One is facing downwards. One is facing upwards. In FCC, the second layer comes on top of the cavity which is facing downward. It occupies this the three cavities which are facing downwards. If you see, there are three similar cavities. I'll erase everything. The three similar cavities are 1, 2, 3. So in order to have the second layer as the closely packed layer, the only thing you could do is that have the atoms at 1, 2, and 3 similar positions. This would be the second layer, layer B in FCC, closely packed. Now, the third option, the third layer is there is one option that the layer A, the atoms could come on top of layer A, or there is another option that the third layer atom should come up and occupy this cavity. In order to have the close packed structure, what do you think the third layer should be exactly on top of layer A or on top of this blue region that I have identified in order to have the closely packed structure?
Sir,
Blue region.
on blue region, sir.
G? Blue
Sir,
region.
blue
Very
region.
good. Very
ABC.
good. Very good. So this third layer would occupy the other cavity which is left in order to have layer C. This would give FCC the densely packed structure. So in FCC, the stacking sequence is ABC, ABC, ABC. This is the way. Now the layer on top of layer C would again be layer A, then layer B, then layer C. So this is how the stacking sequence in FCC continues. Let us see in a unit cell how these atoms are arranged. Since all these layers would not fit into a unit cell, let's see, you'll not be able to see the complete layers, especially for layer C. लेयर सी में आप कंप्लीट लेयर नहीं देख पाएंगे एक यूनिट सेल के अंदर. देयर आर मल्टीपल यूनिट सेल that would form this layer C. So let's say this is an atom situated in layer C, and you would have another unit cell having the same atom and another unit cell having the same atom. This is layer C atom. The layer B atoms within this unit cell are situated in this way. So this is the layer B atoms. If you could see in 3D, this point is above these points which are in layer B. And then you have layer C points which are, or layer A points which are below this red layer, which is the layer A. So different unit cells would form layer A. This is again, if I could remove thing, this is your layer A. On top of it is layer B, and this layer A, since there is only one atom in this unit cell, I cannot draw the plane itself because there would be another atom over here, some atom over here. This would form the layer C. But since we are sticking to one unit cell, I'll not be able to draw the complete plane for layer C. If you looked at these triangular planes, they are the close packed planes in an FCC unit cell. And if this is my origin, these planes are essentially 111 planes. These are known as 111 planes. These are the closest packed planes in an FCC crystal structure. I hope it is clear to you guys.